And so here we have the fundamental theorem of calculus is our next talk. And so the big thing what we're going to be using here is our telescoping sum. And so basically what we're going to note is, if you notice, where is it? So if you remember this telescoping sum, right? This, if you remember, this was just nothing more than an minus a0. And I told you this would probably be something good to go over and like test out and see how this works. Well, if you notice this little part here, notice how when we're looking at our integral, this is almost the same thing, right? So we have some integration here, some definite integral. Here we change it to the Riemann sum notation. And then here I'm going to change this delta xi to what it actually represents. And notice here how we almost have the same thing. And so it seems like I should just be able to take something at the beginning or something at the end and something at the beginning, and I should be happy. Now, this is not 100% the same, so these two are not the same. Not the same. Why? The reason why is because I have this f of xi star, right? So really, they're not the same, because when I try to multiply, right, f of xi star, xi minus 1 plus f of xi minus 1 star xi minus 1 minus, here I can't actually cancel. So normally up here I can cancel, right? So I normally have ai minus ai minus 1 plus ai minus 1 minus ai minus 2. And these two can cancel, but here I can't. They're similar, and they use this idea in order to prove what's called the fundamental theorem of calculus. And so let's highlight this because it's fundamental. Sorry. And so what we're going to first recall, before I actually state this, is what an antiderivative is, right? So if you recall that an antiderivative, so if we start off with some function f, then the antiderivative is any function f of x whose derivative is equal to f of x. And we're going to use this for the fundamental theorem. And basically it's saying that if f is continuous, is a continuous function on some closed interval ab, and if big F is an antiderivative of f of x, then this is nothing more than f of b minus f of a. That's it. This is the fundamental theorem of calculus. This is gorgeous because it basically says, well, to calculate this, I just need to find an antiderivative, plug it in at the beginning and the end, and subtract the two. That is super weird. So another thing I'll note is sometimes what we write here is I'll write this notation, f of x, and you've probably seen this before as well, f of x from a to b. So these are two different notations. They mean the same thing. And so why is this weird? So for example, if I have some function, what basically it's saying is, so if I have an a and a b here, what this theorem is saying is that the area here, so if I take the area here, this is equal to taking the finding some function whose, so here I would have some function that's positive, right? Where here, this is positive as well. So I have some function up here, and if I take the value here and here, so here this is my function f of x, whose derivative is the same. So this slope here is equal to this point. This slope here is equal to this point, right? So this is f of a, f of b. And somehow these points tell me something here. This is super bizarre. If you didn't understand this, don't worry. It's not very understandable because it is super weird. And so what do we have to know? What we're going to have to know is we need to figure out some antiderivatives, right? So we need to recall our antiderivatives that we talked about on Monday, actually. Wow, we've been going so fast. Sorry that this is so fast, especially since it's online. Yeah, if you guys have any questions, like, do not hesitate. Do not hesitate to ask me. I know there's probably a million, so make sure to ask. Online is never easy. Anyway, so I digress. So we need to calculate some antiderivatives. So some of these we've already seen before, right? So like x to the n, remember we can just add 1 to the exponent and divide. And remember the way to test these out is to actually take the derivative. So here I can take, right? So if I take the exponent, I bring it in front and I subtract 1 from the exponent. These would cancel and I get x to the n. So this works for everything except for x to the minus 1, whose antiderivative is actually just this. We can do the same thing with sine of x and cosine of x. Even secant squared of x, right? So this should just be tan kx over k. We can do the same with cosecant, with secant of tan, etc. We can even do e to the kx, right? So e kx. So what does that mean? What that means is we have an easier way to solve our integrals. And I just dropped my pen. So for example, let's look at the example we were just doing earlier, right? Remember how it was disgusting and long. Notice here how it's significantly easier. So what do we have? Is I start off with my integral, right? Here's my integral. So remember how this is equal to the limit as n goes to infinity, summation I equals 1 to n of f of x I star, which I guess technically is just squared, so I can just replace this right away. Squared delta xi, right? So this is equal to that. That's what we did. And so here, if I look at my thing, so I'm going to have to find my antiderivative. So antiderivative of this is just this function up here, right? It's x to the n. So here we should get x to the n plus 1, so x cubed over n plus 1, so cubed. So notice how I have that here. And I'm taking that from 1 to 2. So let me go back quickly. Sorry for jumping back and forth. But let me go back and remember that I have this, right? So I take my antiderivative and I take it from a to b. And this is nothing more than f of b minus f of a. And so let's look at this. So here I have this, right? So this is nothing more than f of b. So f of 2 minus f of a. F is x cubed over 3. So I have 2 cubed over 3 minus 1 cubed over 3 is equal to, so here I have 8 over 3 minus 1 over 3. So 8 minus 1 over 3, 7/3. So notice how I get the exact same response. This is so much easier, like ridiculously easier than what we did earlier, right? And so we're going to use this method when we're calculating integrals. Here I'm going to remove this so I can do, actually we'll do this. So let's try the next one. Here I have 2x. So remember I can bring a 2 out. 2 to the 4x dx. So here x, I can use my x to the n, right? So here n is equal to 1. So I have 2 x squared over 2, and I'm taking that from 2 to 4. Yeah? So here I plug these numbers in, so I get 4 squared over 2 minus 2 squared over 2. Notice what I did here. I put in parentheses and left the 2 outside, because when I'm multiplying here in the middle, this is for all of this, right? It's 2 times this entire thing. And this thing in the middle is this negative. You have to make sure to remember this. When I taught integration before, a lot of people would forget these parentheses and then forget to distribute this 2. Remember these parentheses. Parentheses are very, very, very important. So here we get 2 times 16 over 2 minus, well, I guess I can just, yeah. And then here 2 squared over 2 is just 2. And so we get 2 minus 8 minus 2, 2 times 8 minus 2, so 2 times 6, which is 12. Okay, that was nice. It's much better than trying to do a limit of a summation. Let's do one more. What time is it? 46 minutes. And then I have that thing. What's after this? Okay. We're a little ahead. So that's okay. Probably because not everyone's here to ask a million questions. I'm sorry. I'm probably, I hate this. Okay, stop. Let's keep going. 2 more examples. Actually, no, we'll stop here. We'll stop here and then I'll go over the next 2 examples on Monday. So you have a little break to think about this. So think about these, finish your exam, do well. I believe in you all. Think about doing pass fail to make your lives less stressful, especially if it's not something you need, especially if you're already near the border. Like it might be something you want to consider. So yeah, this could be a better option for a lot of you. So yeah, hopefully everything is going well. I love you all. I miss you all. Stay safe, stay healthy, stay indoors, unless you need like pharmacy and or food stuff. Tons of love. Bye.